Hello, here we are at a lecture, are we at 14 already, on series, and this is the comparison test, and hopefully I fixed my mic so I'm a little bit louder and you don't have to turn your computer up all the way to hear me. So the comparison test, let me just point out, there are two classes of series right now that we know the convergence or divergence of. Geometric series we know really well. We know when they converge, when they diverge. P-series we know really well. Well, we know pretty well. We just learned them, but we know them pretty well. We know when they converge and when they diverge. So the next two tests we're going to get, the comparison test and the limit comparison test, are ways to compare other series to these series. So the idea here is we're going to have one of the series we know whether it diverges or converges, and another series we're looking at. So suppose we've got two series with positive terms. It's necessarily positive terms, so you've got to make sure you've got that. And suppose you know that the terms in the first series is always less than or equal to the terms in the second series. Okay, so remember, if they're positive terms, what are the two options? The options are they converge or they diverge to infinity. They just get bigger and bigger and bigger. You're not going to have any back and forth action here. So if the bigger term converges, right? If the bigger series converges, well, that means the smaller series can't go off to infinity. It must converge as well. And then what's the other direction? If the smaller series diverges, if we know the smaller series diverges, then the bigger series has to keep getting bigger and bigger and bigger. It has to diverge as well. Okay, so the comparison test is, well, if you know something converges or diverges, and it's in the right order, it's something smaller. If you know a series that, if you've got a series and you know it's smaller than a series that converges, then that series is going to converge. If you've got a series and you know it's bigger than a series that diverges, that series is going to diverge. So let's look at some examples here. So this first one, well, the first one, you should look at it, and both of these comparison tests, the big issue is trying to figure out what series to compare it to. So let's look here. This one here, we've got, that looks an awful lot like a geometric series. So what geometric series? Let's compare it to this series, 2/5 to the n. So does that converge or diverge? That converges, right? Because 2/5, that's a geometric series, and 2/5 is between -1 and 1. Furthermore, not only does that converge, 2 to the n over 5 to the n is going to be bigger than 2 to n, bigger than or equal to 2 to the n over 5 to the n plus n, because you're just making the denominator bigger. When you divide by a bigger number, you get a smaller number. So therefore, since this series converges and each of the terms in this series is bigger than or equal to each of the terms in the original series, that tells us the original series, 2 to the n over 5 to the n plus n, converges as well. By the comparison test. Now let's look here. Again, what do we want to compare this to? Well, it looks an awful lot like a geometric series again, but it looks like this geometric series, 5 over 2 to the k, which what? It diverges, right? That series diverges because r is equal to 5/2, which is bigger than 1. But also, what else do we know? We know that 5 to the k over 2 to the k is less than 5 to the k over 2 to the k minus 1, because I'm dividing by a smaller number here. I'm going to get a bigger number. So that tells me this thing is diverging as well. Okay, now I put this next example in as an example of when we can't use this comparison test. This is going to be when we use this limit comparison test on, not the regular comparison test. Because what would we like to compare this to? We'd like to compare this to 2 to the I over 5 to the I, right? We would like to compare it to that. However, this converges, right? And so in order to say this converges, we would need our terms to be less than or equal to that. But the terms aren't. The terms are, in fact, bigger than that. So this doesn't tell us, this test doesn't work with this. So this test doesn't work with choosing this series here. You might be able to find something that you can say is bigger than it, but that's going to take a lot more work than the next test. This is going to be one that we're going to use the limit comparison test on. Okay, now let's look at this next one. Well, this next one, that cosine squared k is a little bit weird. Notice I don't have a beginning or starting. Beginning, I don't say where I'm starting from, k equals blank to blank. When you're talking about whether something converges or diverges, we really only care about, we don't care about the first few terms. It doesn't really matter where you start from as long as everything's defined. So often we'll just leave out the endpoints. Now, what do I want to compare this to? Well, I think we can compare this to this. Cosine squared k. Well, cosine squared k itself is always less than or equal to what? It's less than or equal to 1. So this whole thing is always less than or equal to 2 over 3 to the k. So the series 2 over 3 to the k, well, that's 2 times a geometric series, right? That converges. Therefore, the original series, cosine squared k plus 1 over 3 to the k, converges. Okay, next one will be the limit comparison test.